Here we're going to look at the dependence of cell potential E on concentration. Standard potentials, E0 values, occur under standard conditions: 1 molar solutions, 1 atmosphere of pressure, and 25 degrees Celsius. Let's consider conceptually how E will be affected by concentrations other than 1 molar. In this picture on the left, we have zinc being oxidized to zinc ion, kicking off a couple of electrons, and reducing copper 2 ion to neutral copper. In the lower right corner, we're going to put the overall reaction equation: zinc and copper 2 on the reactant side, and zinc ion and copper on the product side. Assuming we're at 25 degrees Celsius, if both of these solution concentrations are 1 molar, then the cell potential is the standard cell potential, which would be the number from the table for this copper reaction, plus the flipped number from the table for the zinc reaction. If we were to check that out, we would get this number that's shown below the setup, 1.10 volts. Suppose, however, we don't have 1 molar solutions. Suppose we have very dilute zinc ion in the left half cell and rather concentrated copper 2 ion in the right cell. How would that affect things? Let's look at the equation in the lower right corner and ask what Le Chatelier would say about these changing concentrations. If we have a very dilute zinc ion concentration and a very concentrated copper 2 ion concentration, wouldn't Le Chatelier say that we would need to shift right to get rid of this concentrated copper 2 solution and beef up this very dilute zinc ion concentration? And the answer is yes. That would suggest that the cell potential for such a condition would be more than 1.10 volts. What if the situation is flipped? What if we have a very concentrated zinc ion solution, 5 molar, and a very dilute copper 2 ion concentration? Again, let's ask what Le Chatelier would say about that situation. If you have a very dilute copper 2 ion concentration and a very concentrated zinc ion concentration, wouldn't that suggest that there isn't a great push to produce more zinc ion because you already have so much of it? In fact, the cell potential for that case is going to be less than 1.10 volts. While we can tell conceptually how a cell potential E will be affected by non-standard concentrations, we just did that on the previous slide, the Nernst equation allows us to determine E under any non-standard conditions, whether they be concentrations, temperatures, or gas pressures. In units on thermodynamics, the change in the Gibbs free energy under non-standard conditions was found using this equation: delta G equals delta G naught plus RT log Q. We've previously learned that delta G was equal to negative NFE and delta G naught is equal to negative NFE naught. Substituting yields this expression: negative NFE is equal to negative NFE naught plus RT log Q. Dividing through by negative NF produces the Nernst equation. And there it is in the lower left corner. E is equal to E naught minus RT over NF times the log of Q, where we have a few constants in there. We have R being equal to 8.314 joules per mole Kelvin. The other constant is Faraday's constant, 96,485 joules per volt per mole of electrons. We also have the absolute temperature, that is the temperature in Kelvin, and then the reaction quotient, Q, which has the same form as an equilibrium constant, basically products divided by reactants. Let's consider again the zinc-copper cells above at 25 degrees Celsius. In the upper right corner, I've printed the Nernst equation, and I've printed the overall reaction equation that we began this lesson with. When the zinc concentration is 1 molar and the copper 2 ion concentration is 1 molar, Q, which is products over reactants, is 1 over 1. Remember that neutral metal, like zinc and copper, does not appear in an equilibrium constant expression or a reaction quotient. So 1 molar zinc ion concentration divided by 1 molar copper 2 ion concentration gives you a Q value of 1. Log of 1 is 0, which means in the Nernst equation, when the concentrations are 1 molar, this term completely falls out, and the cell potential is just the standard cell potential of 1.10 volts in this case. What about when the zinc ion concentration is very low and the copper 2 ion concentration is very high? One more time, what would Le Chatelier say? Look at the equation in the upper right. High concentration of this, low concentration of this, strong push to the right. We expect E to be higher than 1.10 volts. Mathematically, Q is equal to 0.01 divided by 5, which is 0.002. If we put all that into the Nernst equation, notice that E naught is the familiar 1.10 volts. We're at 25 degrees Celsius. There's Faraday's constant, and there's our log of Q. If you type all that in, that's the number you get. Positive 1.18 volts. Just as we predicted, a higher cell potential than the standard cell potential. On the other hand, if the zinc ion concentration is very high, look at the equation in the upper right. If the zinc ion concentration is 5 molar and the copper 2 ion concentration is only 0.01 molar, there's a very weak push to the right. In other words, we expect a cell potential that is less than 1.10 volts. Q in this case is products over reactants, so Q is equal to 500. 5 divided by 0.01. If we put the values into the Nernst equation, notice that E naught has not changed. The only thing that's different is the log of Q. If you go through the calculation, sure enough, it is still spontaneous, but it has a lower cell potential.